Afshin Odabaee is kind of like that friend that comes to help you move to a new place and somehow manages to cram all your stuff into the undersized moving van that you rented. The difference is that Afshin crams a whole lot of power and functionality into tiny packages. He was one of the original engineers working on Analog Devices' MicroModule Regulators some 14 years ago, and their ability to pack more power and performance into a smaller space has only improved over time. Welcome to Tech Chats, Afshin.
Thank you for having me and having the team. We appreciate it.
Okay, so what is a micromodule?
A MicroModule Regulators idea came from the fact that DC-DC circuits are difficult to design. I have a video to go with it about what the MicroModule storyline is and what it does. Let's grab a PCB. Let's grab a discrete DC-DC solution, inductors, capacitors. What we are doing, we contain all of them in a package. And different designs, different packages. As I'm showing this video, people see that. What you see right here is the device with the heat sink inside for better thermals. And we do different heat sink designs, different internal design. That's why the top looks differently. We have devices, we call them, let's say, smart, because EEPROM on board. You can digitally read, write, and store data. And there are products where we call them very tiny. They're extremely small, 4 by 4 millimeters, 6.25 by 6.25 millimeter packages. And we extended the power level to higher current, 50 amp, 60 amp. We have a device we just released, 100 amp. We're looking at a 200 amp products in near future. The design itself has every component qualified inside the micromodule. Everything is qualified before we ship a product out to a customer. And our qualification process takes a long time, year to almost sometimes 2 years, where we can design a product in 6 to 8 months. Our qualification is very strenuous and extends to many angles to satisfy a lot of our customers who are in the, let's say, defense, maybe the data centers, and all of these designs do require highest integrity on the reliability. So we spend a lot of money and time on qualification of the components inside the micromodule and micromodule as a whole device.
So let's talk about that qualification process and what it means for designers in terms of reliability of the micromodule.
This is just a snapshot of some of the data that we collect, and it's a live document. Live meaning the data is still being collected as we ship products to our customers. The data is still being collected as we introduce new products. And I will say I'm grateful to our quality team, reliability team for it. Just give a snapshot of what we do. It makes a difference between us and our competitors, if I may say that, is the testing on the quality and reliability. And there are failures. We catch the failures on the components and we start all over again. And one of the tests we do is extremely abrasive, I would say the right word, is the thermal shock. This differentiates from temperature cycling, temperature shock. It's usually is air-to-air industry standard. We do liquid to liquid. So liquid cold, we dip the micromodule in it, get it down to minus 65. Immediately, we dip it in 150 degrees C oil bath. Take it, heats up, take it right back to the cold again. So we go back and forth and we look what cracks, what opens up, what fails, what's peeling off. And here we go again. If something fails, we go back again, redesign it. So since 2006, we have learned a lot. And what we have learned is a lot of many things not to do. And for example, what kind of inductors not to use. And we go back to our suppliers of inductors, work with them to improve their products, the ceramics, capacitors. So we learned a lot. We go back to our suppliers, teach them, and we qualify their production to make sure their product meets our criteria to get inside the micromodule. What does it all whole thing mean? It means the fit rate is less than 0.4. It's critical because if you look at some of the single ICs, silicon in a package, just pick something out there. Most industry standards is 1.25. So acceptable is 1.25. That's single silicon in a package and lead frame. MicroModule is very complex design. It has many materials, different materials. It comes with different materials, and all those together, all that combination goes inside the MicroModule as one unit, is tested. That reliability is 0.4. And this number and the data that we're showing again here and as available to our customers is what gets this product designed in the most strict, high reliability systems in the world. So I would say that would be a main difference versus discrete solution. The user has to buy components separately, maybe qualify each one of them separately. Maybe one product goes end of life. Let's say inductor goes end of life or the MOSFET goes end of life. They don't have that issue with the MicroModule. All that is contained. All that responsibility is up on our shoulders.
And you got some more detail here on power cycling. So what are you doing there that's unique?
Power cycle, now you're talking electrical tests right now, and one of the many electrical tests. This is something else that we disclose to our customers, and it gets a lot of attention for the details we spend, and the data comes out of it is extremely helpful for us to improve products one after another throughout this many years. Power cycle, in essence, is you have the product started up, you turn it on. Power cycle, that means power it up, heats up, starts switching, starts regulating, starts doing what's supposed to do. And we raise this ambient, the junction temperature because it's heating up. We start it up, power it up, heats up, shut it down, cools off, start over again. So this is done 50,000 times on average. We have a device we have done 100,000 because we have to really stress it out because of its unique packaging design. Brand new, no one has done it. We want to make sure that we catch everything we can. So 3 different lots, 50,000 cycles each. So we do 10,000 cycles. We stop. We look at the parameters, electrical parameters. Does the regulation look good? Accuracy? Do we have good enough of the line and load regulation, as an example? Basically, it's meeting the datasheet sheet specs. Yes, good. All right, let's go. 25,000. Stop. Do the same measurement. Do 50,000. Stop and do it. In between or at the end, any of the parameters are swinging around, dancing around, is not meeting the criteria of the data sheet, we stop. Then we got to look at it, what happened. Could be mechanical. It could be just electrical stress. Could be thermal. The whole aim is the bullet number 4. We want to expose whatever element inside the micromodule or outside of it. It could be a solder to the PCB attached. Is a weakness there? What is it? We got to quantify, identify and quantify. We have to be able to measure it for the next micromodule. And we have learned a lot. Despite all those years and 150, 160 products and many millions of power cycles, we're still learning because we are still pushing the boundaries on the packaging and assembly, electrical. We're doing 3D design now, not 2D, multiple layers. The power cycle is a very key point for us.
Obviously, there's more to the story than just reliability. So talk about these innovations you have and how they help designers.
So left to right, just quickly. Cooler operation is a packaging and assembly technology we have developed. It's a secret sauce that the analog devices has. What, in essence, these devices, we call them COPs or component on package. On the substrate, you have MOSFETs, DC-DC, capacitors, resistors, all laid out. The inductor goes on top. This device with the inductor on top has a lot of surface area. That surface area allows our product to be cooled much faster than normal standard product where a lot of heat is dumped into the customer's board. So our devices do not dump the heat as much into the customer's PCB. As a result, we can do higher powers. Our devices are a current mode architecture. Current mode allows the user to add one micromodule to another one to increase current. So this is a 100 amp design. I'm showing you one micromodule. This small little black rectangle you see is 100 amp. So 8 of them, 800 amp. And current sharing is critical, especially accurate current sharing. Third column, ultra thin. Oftentimes the top side of the PCBs are pretty much occupied. Backside of the PCBs oftentimes are left bare. Of course, sometimes people have capacitors, bypass caps on the back, understood. But rarely people think power go on the backside, a micromodule going on the back. So we have a very thin packages designed specially for this purpose to go on the back of the PCB for PCB assembly. Yes, it can go through secondary flow, and some of them are as low as 1.3 millimeter. We have one new device we just released, a 1.18 millimeter tall. Let's go to the fourth column, silent switchers. In essence, we have 2 inputs come to the silicon, and those inputs where the current flows we managed to have the current flow in opposite directions, as you see in the screen. Opposite directions creates opposite magnetic field. Opposite magnetic fields mostly cancel each other. Not 100%, but it is very low. So we grabbed it, the silicon, we put it in the micromodule. The more symmetric these current flows and the routings are, the better, the lower the noise is. So we can almost get close to perfection. If we grab the silent switcher silicon, put it in a micromodule substrate, do the layout, choose the components precisely, and we can make a micromodule regulator extremely low noise, but still be able to power the load. Lastly, digital telemetry is PM bus as the protocol. You basically are telling the micromodule what to do. You can set the output voltage. You can tell it when you turn on, turn off. You can tell it how fast to come on, how fast to turn off. You can also read from it, reading the output current. You can read the output voltage, then calculate exactly how much the load is consuming. There are multiple ways to read data and also write data. And third one is store. There's a storage memory. So the last event is recorded inside the micromodule's memory. But it has that capability, read, write, and also store. It's a wonderful way to do prototyping, and also a wonderful way to control power consumption, and also be able to take your pulse of your system, health of it.
We also have a bit of MicroModule history showing the progress you've made over the years.
Let's go from left to right. The final product is on the bottom. I'm showing the picture on the bottom, LTM4601. The top one is we have not put the mold compound on it yet. This is a 15 by 15 millimeter package, roughly 10 amp. So 15 by 15 millimeter, 10 amp. Of course, we can do 20 amp, 30 amp, 50 amp, but it would be maybe in 20 by 20 millimeter package. But how can we do this without penalizing customer on PCB? We found a way to do it. And this problem to solve was heat. Can we do higher power? We'll make our package so thermally efficient that the package can dissipate heat from inside to the outside. So the way to do it is the invention of this, looks like almost like Star Wars ship here. So it's a heat sink element, and the MOSFETs, instead of being planar 2D, we did 3D. So they're stacked FETs, and we put the heat sink on top, basically touching the FETs, touching the inductor. That's where the heat is generated. So that area that's exposed is where the heat is going to be transferred from inside to the outside. As long as outside is cooler, the thermodynamics principles tell you the heat is going to move. The 10 amp design is 15 by 15 millimeter. The 50 amp design is 16 by 16. So it's almost identical PCB area, but 5 times the power capability. We said, okay, the inductor have mass to them. If we can generate a differential in temperature, make the inductor cooler, and if it's big enough, if massive enough, we can move heat. So this is what we did. This is the first real 3D design for us. So a substrate, DC-DC silicon is inside. The MOSFETs are here too. We put this copper clips very close to the MOSFET, so the heat and the electrons don't have to move far for impedance purposes, both thermal impedance and electrical impedance. We put the inductor on top. With the air flowing, it cools very nicely and generate more power, operate higher efficiency, run it cooler. We don't have to sacrifice one for another. This is still 16 by 16 millimeter package. Come 2-3 years later, after the first try, COP, we came up with this device that you see, LTM4700. What you see on the top is the inductor. As a matter of fact, 2 inductors, but in one package. This is 15 by 22, 100 amp. Let's go back here. I said 10 amp, 15 by 15. This is 100 amp, 10 times, 15 by 22. Again, not much of a penalization going on here. And as a result, we have done different designs, different currents, different sizes, and going down even lower current. Let me show you one example of what I just said. Bottom shows 3 demo boards. There are 4 micromodule regulators, 10 amps on each. This is roughly 100 amp design. So that's the size difference because of the thermal capability. Of course, nobody would use that design. Back then, 20 amp was a lot. And nowadays, on average, I get 600 amp, 500 amp to 1,000 amp design requests coming through. How do we do this? Instead of having a one big 1,000 amp heavy micromodule regulator where the heat is concentrated, Can we dissipate and spread the heat? The answer is yes. So this device I'm showing you as a circuit, as 8 of them, 8 LTM 4700s. Each 4700 is 100 amp, but 12 volt in, 1 volt out, 350 kilohertz. The frequency matters too, of course. The efficiency is good enough, and well, it's never good enough. Unless it's 100%, nobody likes it. So a few years ago, this would be 83, 84%. So we bring it up to 90, 91, and then the packaging. The COP capability allows the device to cool itself, and you can cool it from the top side with the cold plate, blow air around it, or immerse it in a liquid. Its cooling is very easy. And so that's the message on this page. Current sharing and the thermal management is very easy with these products.
What's special about your digital telemetry capabilities?
So this is, again, as on the PM bus protocol, uses I2C bus. The silicon for the I2C EEPROM and the memory is inside the micromodule. What we differentiate ourselves is the accuracy and testing we do. And because of the accuracy, it's more acceptable for especially low voltage applications where you're talking about 0.5, 0.4 volt at 800 to 1,000 amps.
We've talked about high power, but you also showed some ultra-thin devices. Where do those get used?
The height of the micromodule and thickness of it is governed by the height of the inductor inside. Basically, that's the tallest component inside the micromodule. And there's designs out there, especially PCIEs, where the top side of the board itself is really dense. The back side is like, we got room there, but you can't put stuff on the back. Why? Because you have multiple of these PCIe boards sit next to one another. So what's the answer? You have to be less than 2.3 millimeter tall to play on the back side. Well, let's say 1.8 millimeter was the answer. Basically, less than 2 millimeter, you can play. And became successful. And we work with our inductor manufacturers, by the way. And there are other tricks we have used in some of these products to make it thin the way it is. And that's assembly and packaging technology. I give those guys a lot of credit for helping us with these products. We found new markets since 3 years ago, especially optical module market for optical communication. I'm talking about QSFP, CFPs, and those kind of devices, OSFPs. These are thin. Less than 1.8 millimeter now is necessary. Even 1.5 is too tall. 1.3s, 1.4s, 1.2 millimeters are the name of the game nowadays. And we have devices for that too. And the one on the right-hand side I'm showing, LTM 4663s, 4691s, those are some of the thinnest and the smallest packages we can offer.
So how does this all benefit designers?
So this is in a series of examples. Of course, I just talked about ultra-thin on the left-hand side, and I have a standard product on the right-hand side. These are quad output products. The left-hand side is a little brother to the LTM 4644. It's a quad 3 amp. The right-hand side is a quad 4 amp. So in order to make it ultra-thin, we have to shave down on the capability of the product per channel. So 1 amp taken out, we can make it that thin. Let's go on the right-hand side. 4644 is one of the best-selling products we got. So 4644 takes out, if you do a discrete way, 4644 is 70% smaller in PCB area. That's the integration side of it. What performance is this? 4644 is 4 outputs, 4 amp each. Those 4 amps, because these are current mode architecture, you can take that 4 output micromodule. You can make a triple out of it. You can have an 8 amp and a 4 and 4. You can make a dual out of it, 2 8 amps. Or you can have a 12 amp and a 4 amp. Or current share the whole thing together, 16 amp. Why this is important? Many ways. First, with having this capability, our customers can now buy one part number, use it in multiple rails around the system. So if there is a 9 amp requirement, you can use a 4644 if you want to. If you have a system, we need 3 2 amps and 1 4 amp, okay, 4644 would be used for that too. So one part number that could be qualified also by customer. One part number could be used to make life easier instead of buying 5 or 6 different parts and trying to do it. And we are also doing higher power version. We're doing quad 30 amp. So that's 120 amp when the current share. So we're going down in the current, we're going up in the current, and we're going to extend that even farther and farther.
Now, I spent some time in an EMI, EMC role, so silent switcher is near and dear to me. Tell me about that.
Silent switchers. Let's talk about that briefly. I have a short video to show, and I'm going to talk to it. The devices that we have for different applications where the switching noise would become problematic, RF and data converters. And traditionally, the switching regulators do emit noise, electromagnetic field. And bond wires are also act like antennas and also getting the energy out. So we took them out. We did the flip chip. We put basically no bond wires, put on a PCB. We're running a current in opposite direction in the micromodule inside, symmetric design. So basically we are containing the electromagnetic energy right inside. Is inside contained. So what does it look like? The red is what you want to see. The blue is what we can achieve. It is quiet. Is higher efficiency, good transient response. With the micromodule, we can do the precision layout because we're doing, again, the micro level of it, very small level, the laser vias and all that. Of course, we sell it as the single ICs. We also sell it with the IC and the capacitors inside. The capacitor means the two input capacitors I showed that are symmetrical. Those are critical in a design to make the noise very low. So that's on the micromodule products where silent switchers come into picture. And for all this that I've spoken, all the technology, PM bus, silent switcher, the last few pages that I'm showing and the part numbers are listed as an examples. And the right-hand side column is the part number. And ultra thin and some of the examples of what ultra thin looks like, silent switchers, an example.
Thank you, Afshin. I think you've packed the information in here just like you packed the functionality into your MicroModule regulators. If you'd like to learn more about analog devices, MicroModule regulators, and find the right product for your next design, click the links in the description or visit Mouser.com. And be sure to check back soon for the next episode of Tech Chats.